Alright guys, welcome back. In this lecture we're going to be looking at Introduction to C Programming. I'm just going to go through some of the basics that you've likely covered for other languages and other classes you've taken. So things like naming of variables, comments, the different data types available to us, then operations. We've got arithmetic operations, logical operations, relational operations, then conditional statements like if statements and switch statements, loops like for loops, while loops, and the do while loop, and functions if we have time for it at the end. We'll see how well this goes. All right, I'm going to jump over to PuTTY, pull up a CSL computer, and get to programming. So I'm going to do all this as a live demo, so go ahead and join me and follow along. All right, all set. I'm back over here connected to Royal 5, and I'm going to be just going over some of the basics. So first up, I'm going to just name this intro.c. Okay, we'll pull this up. Need a main function. I'm going to be printing stuff out, so I'll need to include stdio. And then first thing I want to talk about is, well, let's talk about variable names. And if I'm going to create a variable, suppose it's of type char, or char. This will hold 1 byte worth of information, typically a character. I can use letters and numbers and underscores when I create variable names. Typically, if it's just a variable name and not a function name or like a constant, it'll be lowercase. So if I want to have just like the letter C for a character, or CH, that's perfectly valid. I can say that's equal to A. I can also begin things with underscores. That's perfectly legal, but I think a lot of the time library functions will use variables that begin with underscores. So it's not recommended because we may see conflicts with other library variable names. You can also include numbers, but they cannot be the first digit. So it's got to start with a letter or an underscore. Capital letters are fine. So this is a completely different variable. They're all case sensitive. So I think that's it pretty much for the variable naming rules. All right, let me tell you a little bit about char data structures. Okay, I just added some details to the file here. The // indicates a comment. So I just got a little section here for variable names. They're going to start with an underscore or letter. They may include digits. They're case sensitive. So next topic is the character data type. So char, in this case, I'm naming my variable ch equals to A. So just a few notes here. Char is typically 1 byte of data. And what this is going to do is it's going to map a character to a binary representation. And that's known as ASCII encoding. So to check this out, one of the things that we can do is just print this out. Printf, and then ch equals, and then here, instead of just writing out the variable, I'm going to do this a couple different ways. We can print out the character using the format specifier, and %c will tell it to print it as a character. So I can do this. I can also write out the character as a decimal value, and we can also write it out as hex. All right, let's just go ahead and run this to make sure I didn't make too many mistakes. Let's put in some new lines. I think that looks pretty good. So we'll go see what lowercase a looks like. So switch to command mode, save and quit, GCC. I typed it wrong. Intro. Oops. Standard IO.h, not C. Oh, I left out something else too. All right. All right. I forgot that main is a function. It needs to return an int. And so down very bottom here, last line, we will return 0. All right. Now did I get it all? Okay, looks good. So now when I run intro, I can see that the character I've selected is A. CH as a decimal number is going to be 97. When I write it out as hexadecimal, that's going to be 61. So this is the ASCII encoding for that variable. Just out of curiosity, go back up here. Let's try capital A. So this was 90. Oops. Lowercase a was 97. It looks like uppercase a is 65. Okay, so this is the ASCII code. In fact, ASCII is in the man pages. We can just look up man ASCII, and then that gives us the entire table here of everything with all of the special characters. So I can see here that hexadecimal and decimal 0 is the null character with only one L capital, or null character NULL lowercase if I write it out. And as I go down here, let's see what we got. Where are the other? There we go. Capital letters over here on the right. Capital A is 65, hex 41. And then lowercase letters are higher numbers. So someone, when they were deciding this, had to make a decision about what order we put these in. It means that when you alphabetize things, anything that begins with a capital letter is going to come first because it's a lower number than anything that begins with a lowercase letter. So here we go, lowercase a at 97. Then they go sequentially. B is 98, C is 99. And yeah, all of them are right here. The digits, like digit 0 is actually ASCII code 48 in decimal and 30 in hexadecimal. So all the characters are here. All right, so I'm going to push Q to quit. One of the things we can do, let me go back and edit this, is because the representation that C uses to store all of the variables is just a binary pattern of bits. We can do math with them. So here I've got capital letter A. I just printed out all of them. Then I can do character equals character plus 1. And I believe that was capital A is a 65, I believe. I could be wrong. I'm blanking on that now. I just saw it. But I can add 1 to that and get character 66. And then I can print these lines out again. Okay, to do this easily, I just want to print them out again. In Vim, I switched to the, in Vim, I can just say the number of lines I want, so I'm going to type a 3. YY will grab those lines. It says 3 lines yanked. Then I can go down to where I want to paste them and just push P, and it prints them out for me. DD in command mode will remove the blank line, so I get rid of that, and there. So I'm going to run this. So we will save and quit, compile, and run it. So yeah, capital letter A was 65. We increment, we get capital letter code 66, and it turns into capital letter B. So bottom line there, we can do math with characters. Just a bit of a cool experiment and a little bit of a review. I'm going to go ahead and make a new file. I'm going to call it char.txt using Vim, and I'm just going to store one letter in here, just the letter A. I didn't push enter, nothing, just the letter A. And then I'm going to put back to command mode. I'm going to write this, quit, and now I should have a char.txt file. I can use that hexadecimal dump, xxd, take a look at char.txt, and just print it out. So what this is going to show me is over here on the left the byte number or line number, and then here I've got the contents of that file in hexadecimal encoding. So the first thing I see here, I put the letter A in, so I get hexadecimal 41 in those two characters. That does correspond to the character A, but then it's not the end. It's gone ahead and added I can't select just those guys. 2 more characters, the 0A there. So it's gone ahead and added, let me pull this back up and see what hexadecimal 0A is. There it is right there. There it is. So right here on line 12, decimal 10 hex 0a is the line feed or new line, so \n. So Vim and pretty much every other text editor out there will automatically go ahead and add a new line to the end of any file that you guys produce. That way, should you do something like just read the file, let's see, cat here.text, it puts the prompt on the start of a new line. So we just see the A, and then it gives us a new line. All right, guys, next thing I want to talk about is the float and double data type. These are used to represent floating point numbers, or things like 1.234. So, and the only difference between them is how many decimal places you get. I believe floats give you 4 bytes worth of data, and doubles give you 8 bytes. And I think that also depends on the machine. So for just me, quick give you a demo. So if I declare a float variable, we'll call it f and say that's equal to 1.234567890. It's going to chop off however many decimal places that will not fit in memory. It's just going to give us the most important ones, and anything with the low significance, if it doesn't fit in the size data where it needs to be stored, will get chopped off. Actually, let me do oops. I haven't used Vim in a while. Forgive me, guys. All right, insert float f equals 1 point. There we go. And then double D. So I'm going to assign the same number to both of these guys. And then I want to print them out. So print f is equal to, and then we'll put in, oops, I need quotes. F equals the format specifier percent f, and then end quote, and then I want f. We'll just see what this looks like. And we'll get another copy of this line, and print out D. Whoops. That one's supposed to be f. This one is the variable that gets replaced, D. Okay, I know it's confusing. My format specifier, f, is to print out a floating point number, and I've got a variable f. I apologize for that. And then D is the double data type, so it should hold more significant digits. Let's go ahead and see what this looks like. So right quit, and then compile and run this. All right. Well, I can see right now I've got a couple things I want to fix. First, this is only printing out 1, 2, 3, 4, 5, 6, 7 decimal places. This one's also giving us only, looks like 7 decimal places. And I forgot the new lines. So let's real quick take care of those issues right now. So I'm going to add a new line for both of these. And the other thing I'm going to do is this format specifier gives me some control over how it's going to print out the numbers for floating point numbers. So the first thing I'm going to do is I'm going to say, give me a field that's 20 characters wide minimum. And then what I want it to do is print this with 16 digits of precision. Okay, I'm going to do the same thing for the double data type. So a field 20 wide with 16 digits of precision. That looks good. Got the new lines. We'll compile and run this. There we go. And now take a good look at this carefully. So the floating point number gives us 1, 2, 3, 4, 5, 6, 7, 8, and then this is where it starts to go astray. So the first 8 digits are right, but the next one was a 9 when I entered it. And now I've got just this random garbage from whatever's in memory that it is printing out next. The double precision number has twice as many bytes, well, both, allocated to it. So it's actually 0, 1, 2, 3, 4, 5, 6, 7. Looks like it's accurate to at least that many decimal places, at least 16 decimal places. Because I should have picked a bigger number. Anyway, I think I made the point. I'm not going to waste your time. Go ahead and experiment with this. Try a bigger number for the number of the precision, and see what you get. Okay, next up I want to talk about the int data type. So int is just going to represent regular integers, just like you'd see in Java or other programming languages. So I can declare an int, we'll call it num, is equal to 14. And now this is going to use 4 bytes. I'm going to write down typically, it depends on the compiler, and the compiler can choose something different. So 4 bytes is the number I used in my demonstration for first part of this lecture, 32 bits. We've also got some other decorators, I guess, short int. So I can just prefix this integer with short, and I get a short number. And what this is going to do, let's just say that's equal to 3, is typically going to be 2 bytes. But again, this is going to depend on the compiler. The only guarantee is that the int type is greater than or equal to the number of bytes available in a short. We can also have a long int. So how about n long equals, and this will give me lots and lots of possible digits. This is typically going to be 8 bytes. But the only guarantee is that it's at least as big as regular int. So it's got at least 4 and maybe more. No guarantee on what it really does. In a little while, I'll show you guys how to actually figure out how long things are. And one other little detail, I don't actually need the word int. Short is good enough, and long is good enough. So I can just write them exactly like this. Let me just, we'll print them out. Print, double quotes, double quotes. Does that look like everything? Let's find out. Still not all of it. Overflow and conversion from, okay. I put too many digits in when I was doing that. So, not quite big enough. We'll shorten that up a bit. Still more problems. All right, now what do I do? Format expects an arbitrary effect int, but it has type of long int. Oh, right. I apologize. The format specifier for a long is LD. So instead of, let's see, where was that line? Right here. I totally got it this time. Watch this. Where's the run? It's been a while since I successfully ran this. There it is, intro. There we go. So now we're printed out the integers. So all I wanted to say there was that I've got some varieties on different sizes that are available to us. Okay, so at this point we've covered all 4 of the primitive data types in C. We've got a char, float, double, and int. And you're probably thinking, whoa, that's it? Where's my string? Where's my Boolean values? If you're familiar with Java, those are used all the time for conditionals and loops. Yeah, C doesn't have those. So quick note on how it does represent those. I mean, they're tricks, but obviously we need those properties. So first up, I want to talk about strings real quick. So what we're going to do is we're actually going to be declaring arrays of characters. So in this case, I can have char. It's going to be a character array, and then I can assign it, a string using the quotation marks. So I can put in CS354. Now if I do it like this, I need to tell it how many characters I'm going to be putting in here. And so it looks like I've got CS354, 1, 2, 3, 4, 5. There's actually a special character that's going to terminate all character strings or character arrays. So I actually need to reserve space for one more. And what this is going to look like when I write it out is I'm going to have a character C, then a character S, then a character 3, then a character 5, then 4, and then there's a special character /0, that's the null terminal character that terminates all strings. So this is just how it's going to be represented inside of C. So I believe this works. %s for a string. Yep, there we go. So that works. I also think that if it's a constant string, I don't need to put in the actual number of characters required. It can count as it's reading my string, and it just does the right thing. Let me double check that while I'm. Yep. So I think I can leave out this 6 right here because it can say 1, 2, 3, 4, 5, 6, and knows that it needs that much space. Yep, that works too. Okay. So as long as I'm declaring it as the string itself. Okay, and just a quick note, I'm using the double quotation marks here to indicate a string, and all of my characters up at the top when I was talking about the character data type, we're using single quotes. So single quotes for a char and double quotes for a string. And I also want to point out too, that char A equals A is very different from char B equals to B. In this case, this is a string, so I need to say it's an array of characters, so I need those brackets. This is actually going to take up, so each char is 1 byte. This one's going to take up 2 bytes. I need 1 byte for the A, and then 1 byte for the \0, null terminal, escaped character. This version right here is shorter. It just needs 1 character for that B. I'm going to use a capital B. So not only different characters, but they're actually different length data structures. The top one takes up more space and requires those brackets. All right, 1 sec, let me go check my notes, see what I want to do next. Okay, so next up, I'd like to talk about the operators that are available in C. There's a number of different types. Oh, okay, I can spell. Number of different types of operators available to us. I'm not going to say a lot about these. They're pretty much the same in every programming language, and by this point, you guys have seen them in Java or Python or somewhere else. But C has arithmetic operators, including addition, subtraction, multiplication, division, and modulo. Exactly like they work in every other language. We have relational operations. That's going to be less than or equal to, greater than or equal to, exactly equal to, and not equal to. There we go. Exactly like every other language. We have logical operators, and those are going to include and, or. So and is the double ampersand, or is the double vertical bar or pipe, and the not operator is just the exclamation point, the unary not. Now let's see, we have assignment operators, and that's going to be the straight up assignment operator equals, so I can say x equals 3, something using that. I can also say x plus equals 3, so plus equals another operator. That'll take whatever's in x, probably 3, and then I can plus equal another thing to it, so it'll add 3 more, say now x is equal to 6, and store it back into x. So we have that for all of the different arithmetic operators. We have a minus equals, a times equals, divides equals, modulo equals. So that's it for assignment. They all work the same. We have increment and decrement operators. So I can have like I++ to take I. If I is equal to 3, I++ will now make it equal to 4. There's also plus I. So that's the pre-increment, so this will happen before the line is executed. The I++ will happen after the line is executed. And the same deal with I minus minus and minus minus I. That's just going to take 1 away. It's going to subtract 1 from the variable I. And then, yep, still recording, good deal. All right, bitwise. I'm not going to do anything with bitwise here right now other than to say they exist. We have a bitwise and, so they'll take all of the bits one at a time and use the AND operation on them. We have a bitwise OR. We have a bitwise exclusive OR. There's also left shift and right shift. And I'm going to come back to these guys and talk about all of those independently. All right, I get them all. Arithmetic, relational, logical, increment, assignment, bitwise. Yeah, okay. And then as far as precedence goes, there's a complicated table. I remember a lot of it. Some of it just kind of makes sense to me. It's in chapter 2, so definitely take a look at the reading for today. Bookmark that page with the precedence if you don't like using parentheses. Otherwise, parentheses will override any of the precedents and you can make exactly what you'd really like to happen work. So, all right. So next up, I want to talk about Boolean values. So Java has a true false, C++ has true false, Python has true false, C does not. Instead, what they're going to do, so Boolean, Boolean, let's just do it this way. For true, let's go with here, 0 is false. Let's do it. 0 is false, non-zero is true. So remember, everything is represented as a number. Just a string of bits. If it happens to be equivalent to 0, then that's going to be false. It could be an integer, it could be a char. If it's non-zero, then it's going to be true. So I'm just going to type up a few examples, and I'll do the first one, and then I'll put in a few more to demonstrate this. So I can write if 1, then what I'm going to do is print true. So, and I'll be right back to talk about conditionals, but let me write this. Oh, right, warnings. I have warnings off. Let me turn this off for a second. There we go. So I've printed true here because it's non-zero. If I go back and edit this and put in a 0 here, oops, I need insert. 0, missed 0. I'll put an end line also. And run this again. So now that it's false, it didn't print out anything. So I've completely skipped that line. All right, let me put some more examples in here, and then I'll just go through them one at a time. And we'll, but you guys don't need to watch me type this stuff. One sec. All right, I'm back. I just typed up some examples for us to kind of go through and explore some of the way Booleans are used as zeros and ones. So 0 is going to be false, non-zero is going to be true. So I wrote up some statements here. If 0, so this should be false. It should go ahead and take the else block here. 0 is false. And then got a little divider here, and then another if 1, then it should print out 1 is true because it's non-zero, so should go to this path. My third example, I picked another number other than 0 and 1. This case is negative 31, and negative 31 is not 0, so this should be true. We should come to this line and say print out negative 31 is true. Okay, and in fact, all of the characters are represented as ASCII numbers. So in fact, A was something like 97. 97 is non-zero, so this statement should evaluate to true and should print out A is true. Okay, same deal here. We can use variables. So I can, I'm assigning the letter X to X, and now I'm using a relational operator, the equal to operator. I can say if X is equal to A, then it'll print out X is equal to A. So in this case, X is not equal to A. It should say X is equals A is false. Now, I've done one little tiny subtle change here. Instead of using a relational operator, I've left off one of the equals. This is a really common thing, a mistake that I make all the time. And this is perfectly valid in C. I can put an assignment statement in here. An assignment statement will return whatever the assigning value is, in this case an A, which is ASCII value 97, and that'll say this should be true. And it will also change the value of y. So y used to be lowercase y, now y will be A. So in fact, let me add one more little thing right here. So after we run the statement, we'll print out y equals, quote, y equals, we need a character, a new line, and then we'll print out y. So So print it out, and we'll see that y has actually now changed to the letter A when we do this example. So let me save this. We'll go run those, and then I'm going to come back for part 2 about short-circuiting the logical operators. So I need to compile this, and then we'll run it. We'll see we're starting right here. So 0 is false, indeed. 1 is true. Negative 31 is also not 0, so true. A is not 0. It's logical, or Boolean, or no, binary 97. So that's true. X equals A is false. Yeah, X is equal to the letter X. A here was the letter A. When I use the assignment, I get Y is equal to A. This actually changes the value of Y, and it returns the value of that binary character A, 97. And so it's going to tell us that 97 is true. And print this out again. So y has indeed changed its value inside an expression like that. All right. Definitely, I'm going to put this code online. Download it. Take a look at it yourself. Play with it. Make some changes. And just experiment. All right. So this next block is about short-circuiting. I don't know if you guys have seen this before, but I use this structure all the time. This is a comment switch. So here, let me just make a little space. Slash star, star slash, and everything between those, this is a comment. Okay? Also, I can write comments where everything after the double slash is a comment. Now, a comment switch starts out with the slash star just like that, and then it's going to end up with the star slash. So it's just like a normal multi-line comment like this one. But what I'm going to do instead is I'm going to go ahead and add a comment. So this line is commented out, the closing comment brace. And then I can turn this on and off by adding or deleting a slash right there. So pretty cool. I like this structure a lot. I'm going to leave it turned off so that it doesn't crash. But I've written some code here that I just wanted to have off. All right, hold on. There we go. That I wanted to have off while I was doing the first part of this. So now I'm going to add that extra slash. That's going to comment out this, begin a giant comment block. And the end of that is right here, slash slash star slash. And now we can use this code. I'm a fan of that structure. Okay, anyway, so here's what I'm doing here. Short-circuiting is the idea, there's a space there, that inside of a Boolean expression right here like this, if I'm using a logical operator like or and, I'm going to take a look at the very first piece of this and decide if this is enough to decide if the whole thing has to be true or not. So in this case, I'm asking if false, or 0, or something else. So if this is false, then I need to go ahead and evaluate whatever's next in order to make that decision. If you look down here, I've got an if 1. So in this case, as soon as I see 1 or something, true or something, I know that this is automatically going to be true. And I don't need to look at the rest of this. And C, in fact, skips all of this. So let me walk through what this is going to do, and then I'll go show you. So in this case, from the beginning, I'm assigning the letter F to a character C. Then if false, so in this case, this is not enough to decide if the whole or statement is true. It needs to evaluate this. So it's going to go ahead over here and say C is equal to T. So this is an assignment statement. It's only got the 1 equals instead of the double equals. So the capital T here evaluates to something in the low 80s, which is not 0. So this is going to be true. So this statement is true. It's going to print out short circuit 0 is true. And it's also going to reassign C to the letter T. So it's going to print out true. C is equal to T. All right. So this one's true, prints out a T. This one's also true, and it's going to print out the F. So let's look at that for a second. So I reassign C to the letter F. And then if 1, so this is true, it's an OR statement. I already know that this whole thing has to be true because the first part right there says it's true. So it's going to take the true path, printf, short circuit 1 is true. but it never goes ahead and evaluates this expression right here, which reassigned the variable c to the letter t. So it's going to stay assigned to f. So when I print out the character, here's the character right there, it prints out an f and a new line. Okay, let me just save and quit. I'm going to compile this and verify that I got that right. Okay, so short circuit 0 true, short circuit 1 true. They were both true, like I said. In the first one, it changed the value to t because it did have to run the second half of that conditional. And in the second case, it did not change it to t. It stayed f because it never had to run the second half of that conditional. So short circuit analysis can be really useful if you have like an extremely complicated math function that needs to run, and you can get around it. So put the easy thing to compute first, the hard thing second. Or if you have something that may result in an error, like the potential for division by 0, you can test to see if it's about to divide by 0, and then only carry through with the division in the second half of the OR statement. That's called guarding. All right, let me pause the video here and pull up the next set of stuff I'm doing. All right, guys, I put together some more code for us to take a look at. So C has 3 different kinds of loops available to us. So I'm starting my loops right here on line 121 with the do while loop. This one's special in that it always does the contents of the loop exactly once, minimum once, and then it goes through and evaluates the condition afterwards. So in this case, I'm declaring a variable I, setting it equal to 3. All this is going to do is print out I, and then decrement it. So it's going to, first time through it says I is 3. I'm going to decrement it. It's now 2. While I is greater than 0, it keeps going. So it's going to print out 2, decrement to 1, print it out, and then go through one final time. So 3, 2, 1. And then when it reaches this line, it'll be 0, no longer greater than 0. It'll stop. So the do while loop here is going to print out 3, 2, 1. I've got the exact code that does the exact same thing using a regular while loop right here. So in this case, I is equal to 3. While I is greater than 0, it's going to print out I and then decrement it. Then print it out again and again. So 3, then 2, then 1. Okay, these work exactly the same way that they do in Java. So I'm not going to say more about them. I've got a conditional statement right here that's evaluated to decide whether this loop is executed or not. For loop, I've got a very simple one right here, very similar to what you can do in Java. So I'm declaring a new variable I. This will only be in scope inside of this loop. I do have another variable I that I was using up here on line 123, but this will be inside the scope of this loop, so this will be a different I from the one outside. While I is greater than or equal to 0, it's going to keep doing this. It's going to decrement I. So first it declares the variables, then it does the lines of code right here, then it checks the condition, and then it, oh, I said that backwards. I said it backwards. Rewind. Mike, focus. Okay, so it's going to declare variables. Int I equals 3 gives me a brand new local variable 3. Then it evaluates the condition to see if I should do anything. I is 3, it's greater than 0, it's going to do this. So it goes through and does the contents of this loop. It's going to print out I, and then it does the post statement, so it decrements it. Now I is equal to 2. Then it checks the condition again, then it does the statement again, then it decrements. Then it checks the condition, then it does the statements, then it decrements until the statement, till the condition here is no longer true. So this one is also going to print out 3, 2, 1. All right, let me just run these and make sure that I didn't screw anything up. And that way, when you guys get the code at home and you're playing with this, no compiler errors. Yep, it's going to work for you guys. 3, 2, 1, 3, 2, 1, 3, 2, 1. And let's go ahead and make just a quick change. Oops, quick change. I want to show you that even if I is, let's make it, we're going to insert -3. The do loop will still execute at least once and print out I before it decrements. The while loop, if I make this -3, isn't going to do anything at all. I'm going to leave the for loop alone for right now. Right? Wait, compile first, then run the code. So the do loop executed once, and then the condition was found to be false and it stopped. The while loop found the condition to be false immediately. I made no changes to the for loop. All right, now I just want to show you something that's cool about C. So in a for loop, whoops, deleted too much. Right, in a for loop, there are 3 pieces to it. I get one declaration statement. And this can be a compound statement. So for example, I could say for I int, so this is a statement, it begins with int, I is equal to 3, comma, j equals 12. So I can declare more than one variable in a single declaration statement as long as they're of the same type. I just need a comma separated list of all of these things. And I need to give them values. When I hit that semicolon, that is the end of my statement. Okay? Then the middle piece here is exactly one statement that gets evaluated and used to decide whether it's equal to 0, which case it quits, or it's non-zero and it continues. So I'm going to use my, let's see, I greater than 0 as my stopping statement, just so I don't end up with an infinite loop. And then post statements is a comma separated list of any statements I want. So I can put in a whole bunch of stuff if I want. I can say I minus minus, there's one statement. I can say j minus equals 3, there's another statement. This is an assignment statement. And then I can even put in something like printf, and let's print out I equals %i, and then j equals %d. That'll be j. We'll throw a new line on the end of that. We'll put some quotes, and then we'll print out I and j. And then when this doesn't require a semicolon here. All I need to do is put a parentheses to close up the for statement loop. And let me see if I made any typos. So I'm going to quit and run. Compile. Oh, it's looking good. And run this. Oh, I didn't print out anything. I've got a mistake somewhere. What did I do? What did I do, guys? For int I is equal to 3, j is equal to 12, I is greater than 0, so it'll be good. Subtract, printf. Hold on, I'm pause the video and spot my mistake. Hold on. Oh, I know what I did. I can see it. So it requires at least one statement inside here. So I've got my loop. I needed an empty statement in order to have a statement inside the for loop. Otherwise, it just skips that. That's what I did wrong. So when you run this, there we go. Now it's working. So I started out at 3. I decremented before I did any printing. So it's now 2. J was 12. I decremented that by, the minus equals 3. So it taped 9 before I printed it. And then it went through the loop again. So the loop contents were actually empty. I was only using the post statements to do all of the work here. This is actually really, let me put it back up so you guys can see this again while I'm talking. This is really common to do in like really old C code. Back in the day when, 60s and 70s, I think, you would actually be connecting to a computer through a workstation. You would have a terminal, one of those little boxes with a keyboard, and the main computer would be somewhere else, the mainframe. You would connect to that and do all of your work. The rate of transfer for statements going back and forth was something like just a few characters a second. It was not fast. And so you'd be sending just a few characters to the mainframe every few seconds, and it was basically about as fast as you could type realistically. And then when you compile code, the early C compilers could maybe do 3 to 4 statements per second. So like the job I was a full-time programmer up until last week. Our code base was 120,000 lines long. That would have taken days to compile. Modern C compiler actually took care of that in about 32 seconds on a modern computer. So it was still a big deal, half a minute to compile the code base. But what programmers would do is they would try and make their code as dense as possible. And if I can squish all of this into one line and it gets processed by the compiler, if I'm doing 3 lines a second, if I can eliminate lines, that's what I'm going to go ahead and do that. So we'll see a lot of statements like this in older code where, up here I was using assignment statements inside of conditionals. I'm just multitasking here. I'm doing more than one thing at a time, and that makes compiling faster, and it's going to generate code that sometimes will run faster, particularly if we can short circuit things that we don't need to compute. So a lot of those things were really essential back before computers were as powerful as they were today. All right, so cool. Last thing I want to do for today is talk a little bit about function declarations. So if I want to call a function, let's say I want to write my own sum function. So last time I was just writing some code that did this right there in main. I want to actually write a function that's going to compute the sum of two numbers. So let's just say int s is equal to sum of, and then we'll go with, I don't know, 1 and 2. So this is a function that I'm about to write. It's not a real function yet. This should give me an error if I try and compile it. So in order for the C compiler to actually take and be able to work with this, to do this, it needs to know, as soon as it reaches this line, what the function prototype for sum looks like. It needs to know what are the inputs and what is the type of the output. So, and that needs to be available before it gets to this line. So what I'm going to do is I'm going to go way up to the top now, and I'm just going to, up here on line 2, I'm going to write the function prototype. This is also known as a declaration. Okay, so it returns an integer. The name of the function is sum, and it takes two pieces of data, both integers, int, we'll call them A, and int B. All right, and then I'm going to just end this with a semicolon. I'm going to do a couple other things too. I don't want to actually change the variables in my function, so I'm going to label these both as const. It's just safe. Anywhere you can stick const not only makes your code go faster, but it keeps you from breaking things you didn't intend to. Functions in C are passed by values, so this is just going to make a copy of the values anyway, so it just means that I won't be able to change these inside of my function. So once I've got the declaration, now as soon as it hits this sum function in main, it knows that it needs to check and see that it's got two variables of type integer, A and B, as parameters, and is returning an integer, so that needs to get stored in a variable of type int. Just needs to know how much space it needs available. Okay, now once I've done this, I'm actually going to put the definition of my function, the part that does the work, at the very end of the function, after main. So right there, that bracket is the closing bracket after main. And here I'm going to put the function definition. So it returns an int. The name of the function is sum. It has a parameter list. Const A, int A, constant B. And now my function definition goes inside of curly braces that define the scope of the function. C uses scoping rules very similar to Java, so braces, anything you want to be grouped together. Variables declared inside a particular scope are retained there. They're not available outside of that. So just like you'd see in Java. And all I'm going to have this do is, here we'll say int result is equal to A plus B, and then we'll return that result. All right, now that I've done something, this won't actually be useful, and we can see that it works unless I print out sum, or I'm sorry, S. So we'll print S equals format specifier for a decimal, a new line, and then S. And that should be the last thing. Last thing it should print out is 3. All right, so let me make sure I didn't make any mistakes. And then we'll run this, and we'll see that S is equal to 3. So just the briefest introduction to functions. We'll be doing a lot more with that as time goes on, but I wanted to give you guys the preview so you could get started using those. All right, I'm going to stop the recording here. I'm going to go compile all these little clips into a video and throw that up on YouTube. And I'm going to take this code, download it, put that up on our course website, and I will be back with you guys later. Have an awesome day.